Hey everyone, and welcome back. Today we are unrelieving one of the most intriguing mysteries in the world of high performance computing, which is how is Redis so incredibly and efficient despite being single threaded. We are talking about a blazing fast, open source in memory key value store that can handle over than 10 100,000 yeah, 100,000 requests per second with just one thread. In a world where multi-core CPUs and parallel processing dominate, Redis seems to defy logic, but it doesn't do that because its speed is a result of a brilliant architectural design choice and a clever optimization. This video we will break down the five key yeah the five yeah okay the five key reasons why Redis is in the in-memory express lane for real-time application. So we will explore here in this one. We will explore first in-memory storage, like data lives entirely in the RAM. Second, we will talk about the single-threaded event loop. Third, we will talk about optimized data structure. Fourth, we will talk about some I/O efficiency, and fifth, we will talk about server-side scripting. Okay. Let's start with the in-memory storage. So, if you want to talk about RAM versus disk, for example, um, unlike traditional database that store their primary data on disk and only load portions into memory as needed, Redis keeps the entire data sets in RAM at all times. Think about it even with a fastest SSDs. Like reading data from disk is thousands of times slower than reading directly from RAM. So when Redis perform a simple get command, it doesn't wait for any disk I/O. It simply follows a pointer in memory and operation that completes in nanoseconds, not milliseconds. This immediate access to data is Redis foundational speed advantage. Second, we need to talk about the memory efficiency. Okay, so Redis doesn't just store data in RAM; it stores it efficiently for small values. Like Redis uses a high compact memory formats like zip lists or int tests, and I would say you don't need to know what this means and what they are doing because in context of system design interviews, you just need to know what these are on just high level. Is that you need to understand that Redis uses highly compact memory formats. That's it. These specialized formats are designed to pack data tightly, which not only saves memory but also improves the CPU cache locality. This means Redis touches fewer memory locations per command, making operations even faster as data stays closer to the CPU processing units. Um, there are some trade-offs we need to think about. The first thing, we have a memory bound capacity. While in-memory storage is the Redis superpower, it's also introduced two important limitations. The first one is memory bound capacity, which is your data size is directly limited to how much RAM your machine has. Like for instance, on a 32 gigabyte of server, 30 on a 32 gigabyte server, Redis can only store roughly 32 gigabyte, not more than that. Maybe minus some overhead. If your datasets exceeds this, Redis will start either picking keys or rejecting write operations unless you scale horizontally. To manage this, Redis offers various key eviction policies like least recently used or LRU, or least frequently used LFU, not U. And also there's random, and also there is evaluate TTL, which is time to live, is the fiction alternative for datasets larger than single machines RAM. You can also shard your data across Redis cluster if you want to save everything. Let's talk about we did talk about the memory capacity. Let's talk about the volatility and durability. So the second limitation is volatility. Basically, RAM is volatile memory. What that means? What is volatility actually mean? So it meaning this this meaning that it loses all its data when the server shuts down or crashes. Okay, this is a significant risk if you are storing critical data long term. Redis, Redis cleverly solves this with optional persistent mechanism, allowing you to write data to disk periodically or in real time to ensure durability without compromising its core performance. There are two ways to solve this problem. There is RDB, which is Redis database snapshots. This method makes a point-in-time snapshots of your entire datasets. It runs a forked child process, meaning the main Redis thread can continue serving traffic uninterrupted while the snapshot is being written. RDB is great for backups and for systems that can tolerate some data loss between snapshots. Also, there is AOF, or append-only file. This mechanism logs every single write operation received by Redis to disk. AOF offers configurable sync options, allowing you to balance durability and performance. Every write basically safest but slowest every second, which is a good balance, or never, which is fastest but quite the riskiest. AF also supports background rewriting to keep the file size manageable. Crucially, both RDB and AOF persistence methods are designed to run asynchronously, ensuring the main Redis thread never be blocked. Okay, next we'll talk about the single thread event loop. So, okay, let's talk about the Redis most intuitive design choice. All commands in Redis are executed by a single thread. I don't know, but if you are familiar with Node.js, actually Node.js is a single-threaded language, so you will see something like that in Node.js as well. So this seems almost absurd in an era of multi-core CPUs and parallel processing. Shouldn't more threads means more performance? Not necessary. Redis proves that sometimes one well-utilized thread can significantly outperform many if the underlying architecture is designed correctly. Okay, let's try to understand how one thread handles thousands of clients. So the let me get my pen because will need it. Okay, so the magic lies in the Redis event-driven I/O model powered by I/O multiplexing. I/O multiplexing is a sophisticated technique that allows a single thread to efficiently monitor multiple I/O channels like network stocks, pipes, or files simultaneously instead of creating a new thread for each client connection, which quickly consumes resources. Redis tells the operating system, watch these client stocks. This one, okay. So Redis tells the operating system, watch these client stocks for me and let me know when any of them have data to read or are ready to write data. Number two, we need to talk about the high optimized system calls. Like this, this is achieved through highly optimized system calls specific to different operating systems. We have the Linux, which is, I guess, a high-performance I/O event notification system designed for extreme scalability, efficient handling thousands of concurrent connections. There is also one for Mac OS, which is a similar BSD-style I/O event notification system that monitors a wide range of events. Also, we have a fallback, which is a select one. The oldest and most portable method that we used as a fallback On other platforms, these interfaces allow the Redis server process to remain dormant, consuming virtuality, no CPU cycles until the exact moment that it arrives on a network socket or a socket becomes writable. So let's talk about the event loop here. So at the heart of Redis single-threaded efficiency is its event loop. This is a lightweight, non-blocking cycle that effectively and efficiently juggles thousands of client connections. When a client sends a request, the operating system notifies Redis via the I/O multiplexer, which then wakes up the event loop. Redis then first reads the command from the client stock buffer. Number two, process the command. Number three, sends the response back to the client. Number four, and then crucially immediately moves the next ready client without waiting. This loop is incredibly light, predictable, and fast. Redis cycles through ready connections, executes commands one at a time, and responds quickly without ever waiting on a slow client or incurring the overhead of thread context switches. But why single-threaded works so well? By sticking to this single-threaded execution model for command processing, Redis skillfully avoids all the typical overhead that plagues multi-threaded systems. There is no expensive context switching between threads, no complex thread scheduling decisions, and most importantly, no need for locks or maybe semaphores or to protect shared data. This eliminates race conditions and deadlocks entirely. As a result, Redis spends almost all its CPU time performing actual useful work rather than wasting cycles coordinating between multiple threads. Also, there is a huge benefit of a single threaded nature is inherent atomicity. Since only one thread is modifying Redis in memory data at any given moment, operations are naturally atomic. This means no two clients can concurrently update the same key in a way that leads to corrupted data. You don't need to implement complex locking mechanism to ensure safety, and you won't get partial updates due to the concurrency bugs. This dramatically specifies Redis internal logic and significantly improves both predictability and latency consistency. Okay. Next, we will talk about the optimized data structures, intelligence data management. Redis isn't just fast because it stores everything in memory. It's also fast because it stores data intelligently and efficiently. It doesn't use generic one-size-fits-all containers. Instead, Redis carefully picks and implements the most appropriate data structure for each use case, all implemented in high-performance C code with an obsessive focus on speed, memory efficiency, and predictable performance. There's one thing that we need to talk about, which is adaptive internal representations. So one of the key optimizations here is Redis use of adaptive internal representations. Each core data type in Redis, like hashes, lists, sets, or sorted sets, actually has multiple underlying internal implementations. Redis automatically switches between these representations based on factors like the size of the collections and access patterns. For hashes and lists, small collections are initially stored as very compact memory formats These formats are incredibly memory efficient and very fast for small numbers of elements. However, as these collections grow larger, Redis automatically and transparently converts them to more scalable structures, okay, which maintain good performance even with many elements, like more structures like hash tables or maybe or even linked lists. Similarly, for sets, if the elements are integers and the sets is small, Redis might store them as optimized, in tests, int sets, or integer sets. But once the set grows beyond certain threshold, it's upgraded to be like a hash table for better scalability. So if you wanna think about the build for big O performance, Redis developer carefully choose implement these data structures to ensure excellent time complexity for common operations. For example, if we have a get set one, this one has constant time, meaning it takes the same amount of time regardless of how much data you have. And also, I guess the push has O of 1, and the remove commands has also O of 1, so everything have O of 1, which is basically, I don't know if you. This is incredibly hard. This is not easy at all, which is incredibly efficient, and also it's efficient. As dataset grows, these operations remain fast even as dataset scales because of Redis efficient internal representation and it's highly fine-tuned implementations in C. Yeah. What we have next? We have the I/O efficiency mastering network communication. So Redis isn't just a fast executing commands internally, it's also extraordinary I always mispronounce it. Extraordinarily efficient at handling network I/O. Whether your application needs to serve a single API call or manage tens of thousands of concurrent clients, Redis can keep up with minimal latency and maximum throughput. So, what exactly contributes to a Redis I/O hours? First, we have a lightweight, fast protocol, RESP. Redis uses its own custom protocol called RESP, which is a Redis serialization protocol. This protocol is deceptively simple. It's text-based, making it easy for human to read and debug, but it's also extremely lightweight and easy for Redis to parse. It's much simpler than parsing a full HTTP requests for complex SQL queries or deeply nested JSON structure. Each part of an RESP message clearly defines the number of elements and their sizes, allowing Redis to read and parse commands with minimal CPU cycles. Next, we have the pipeline, which is batching to boost throughput. One of Redis' most effective I/O optimization feature is command pipelines. Normally, when a client sends commands, it sends one command, then waits for a response, then sends the next. This works fine for a few requests, but is highly efficient when you need to send thousands of commands. With pipeline, the client sends multiple commands in a single request without waiting for intermediate response. Redis then reads and queue all these commands, executes them in order, and return all response back to the client in a single go. Next, we have Redis 6 Plus, which is optional I/O thread. While Redis traditionally used a single thread for both command execution and I/O, Redis 6 introduced optional I/O threads for further enhanced performance, especially in network-heavy scenarios. When enabled, these detected I/O threads handle the heavy lifting of reading client requests from sockets and writing response back to client. Crucially, the actual command execution still happens on the main single thread, preserving Redis core atomicity and simplicity for data manipulation. This hybrid model delivers the best of both worlds: multi-core processing for network operations combined with the simplicity and atomic guarantees of single-threaded command execution. And lastly, we have a persistent connection. Redis client libraries typically use persistent TCP connections. This means that once a connection is established, it's kept open for subsequent commands, avoiding the overhead of repeated TCP handshakes and reconnections. This leads to lower latency for every command and more predictable performance under high load. Persistent connections also reduce CPU and memory usage on the Redis server itself, as it doesn't have have to constantly allocate and delocate resources for new connections. I guess we have, yeah, this is a lot of things that we'll talk about. So finally, another powerful feature contributing to Redis efficiently is its ability to execute server-side script using LOA or LOA. I call it LOA. I don't know if it rhymes or not. This allows you to run complex application logic directly inside the Redis server, eliminating multiple round trips between your client application and the Redis servers. The problem with multiple round trips, imagine you need to perform a sequence of operating check if a user exists. If they do, increment their score and then add them to a leaderboard, and finally returns the new score. If you do this with a separate client server request, it involves first multiple networks round trips, introducing latency. Second, potentially race conditions if multiple clients try to perform this operation concurrently, leading to incorrect scores or leaderboard positions. Third, more complex code on the client to manage the multi-step logic and ensure atomicity. The lowest scripting solution, I guess this is an example for it. With Lua scripting, you can encapsulate all this logic into a single Lua script and execute it as one atomic operation entirely on the Redis server. For example, a Lua script could increment a user's score and update their position on a stored set leaderboard. You then execute this script using the eval command, passing in keys and arguments. If you can look at this one, you would run this script, I guess, with eval and you put the script body, and you put user 123, and you put the port. This single command automatically increments the user's scores and updates the leaderboard directly on Redis server. Lastly, we have use responsibility. Responsibly, not responsibility. While incredibly fast and atomic, it's crucial to use Lua scripting responsibly. Since scripts run on Redis main single thread, a slower or CPU intensive script can block Redis from serving other requests. Therefore, it's vital to avoid unbounded loops or expensive computations within your scripts and to keep them short and predictable. Okay, so we are in conclusion. So the seemingly paradoxical speed of Redis, despite being a single thread, isn't just a magic trick. It's a symphony of incredible smart design choices we did talk about, and that it's in memory storage. Number two, the single thread event loop, and I would say this is the most important one. Number three, it's optimized data structure. Number four, the IO efficiency. Number five, the server side scripting. So yeah, thanks for watching this video. And if you like this video, give it a like, subscribe, and hit the notification bell so you'll never miss any. You guys in future problem.